Good evening, Moffat. This is Warping Space and Time. As you can see from the little subtitle, I'm talking about the science fact and the science fiction of black holes. Mostly fact, a little bit of fiction. So I'm going to be covering a brief history and very much a brief history of black holes, and then looking at the facts, which is most of the talk. And then at the end, I'm going to have a little look at science fiction and then think for the last couple of slides about the future. So a brief history. So let's just remind ourselves that what are black holes? They are a region of space from which nothing, not even light, can escape. And a lot of people might think that black holes are a recent concept in the sense of perhaps the last few decades or perhaps from the middle of the last century. But actually the idea of a black hole goes back much further. Back to 1783, the Reverend John Mitchell, who basically said if we take a large enough mass, then perhaps all light emitted from such a body would be made to return toward it by its gravity. In other words, he had the first idea that if an object was massive enough, gravity might stop light escaping. So that was in the 1700s, but during the 1800s, all ideas of such so-called dark stars was basically ignored. And it was a century later, more than a century later, before the idea was resurrected. And during the 1900s, there was an explosion of interest. I'm not going to cover all of the contributions from these great people. Some of them you may recognise. I put names and dates there so that if you did want to go away and do a bit more digging to see a little more detail, you can do so. But it basically got kick-started with Einstein in 1915 and his general theory of relativity. When other scientists started applying Einstein's equations, they started getting some very odd results. So, for instance, Schwarzschild determined that if you take a large mass and compress it to a small volume, a volume whose radius has now become known as the Schwarzschild radius, odd things start to happen, including, amongst many other odd things, time apparently stands still. And that's why, as well as thinking of these objects as being dark because light doesn't escape from them, some people also started labelling these objects as frozen stars because time stops at a particular radius when you take a large mass and compress it to a small volume. What we need to understand black holes, or at least to get a handle on black holes, are four different concepts, and I'm representing these by four pieces of the jigsaw. I said from definition that a black hole is a region of space from which light cannot escape. So the first thing we have to deal with is what do we mean by escape velocity? The second piece of the puzzle is thinking about what Einstein had to say about space. We're not going to go into the details of general relativity. You'll be glad to know we're not going to be dealing with the maths, just one or two concepts that will help us understand what black holes are. The third piece of the jigsaw is knowing where black holes come from. Massive stars towards the end of their life might form a black hole, so we'll have a quick think about that. And the final piece of the jigsaw is how do we detect the existence of gravity, such as the intense gravity around a black hole. So those are the four pieces of the jigsaw that we need to think about. We're going to look at each of these pieces in turn. It doesn't actually matter in which order we do them because they are almost independent, but I'm going to cover them in the order I've just mentioned. And I'm going to stick to this particular colour scheme, and for each section, starting with escape velocity, I'm going to put this icon in the top left, so that all the slides for the next few dozen slides are going to have this icon in the top left to remind you which particular piece of the jigsaw we're dealing with. That might help you as we go along during the talk. It might help you if you're watching a recording of the talk, and the icon is there in the handouts again, such that if you jump into the middle of a handout, you can see which section we're dealing with. So escape velocity. The escape velocity at the surface of a body depends only on the ratio of the mass to the radius. If we imagine that we're standing on the surface of a spherical body, let's not worry about potato-shaped asteroids and things like that. If we're standing on the surface of a spherical body, then the velocity at which we need to throw an object for it to escape the gravity of that object only depends on the ratio of the mass of the body we're standing on and the radius. So if I wanted to take this pen and throw it away from the Earth, so it left the gravity of the Earth, ignoring of course things like air resistance, there's a particular velocity with which I would have to throw this pen. It doesn't actually matter which direction I throw it, it doesn't matter if it's straight up or sideways, it's the same velocity regardless. Strictly we ought to call it an escape speed, but it's become known as the escape velocity. We can calculate what the escape velocity is for any mass and radius, and we find that the velocity to escape from the surface of the Moon is about 2 kilometers per second, or about 5,000 miles an hour. That's a lot less than the escape velocity from the Earth, which is about 11 kilometers per second, or about 25,000 miles an hour. So the Apollo astronauts on the way to the Moon had to leave the Earth with a velocity of something like 11 kilometers a second to escape Earth's gravity in order to arrive at the Moon. Coming home was easier because you only need an escape velocity of some 2 kilometers per second, and so with a smaller craft and a weaker gravity, it was a lot easier to leave the surface of the Moon than it was to leave the surface of the Earth. A Saturn V gets them off the Earth, but a relatively small rocket engine gets them off the Moon. If we continue and think about the escape velocity of the Sun, it's a larger radius but a much larger mass, so it has an escape velocity of 600 kilometers per second, or something more than 1,000,000 miles an hour. That might sound ridiculously fast, but remember, it's only a tiny fraction of the speed of light. But if the escape velocity depends only on this ratio of mass to radius, we can do a thought experiment and say, what would happen, hypothetically, what would happen if we took a body and we don't change its mass, but we reduce its radius? We take the mass and we compress it into a smaller volume. M stays the same, R gets smaller, so M over R is going to increase. What would that look like? Let's take the Sun and compress it to smaller sizes and see what happens to the escape velocity. So here's escape velocity plotted vertically as a function of the radius of the Sun plotted horizontally. So there's the actual radius of the Sun and the actual escape velocity. But hypothetically, if we were to make it only 30,000 kilometers in radius, the escape velocity would go up to some 3,000 kilometers a second. And similarly, if we were to reduce the Sun to the size a little smaller than the size of the Earth, up goes the escape velocity again, because it depends on M divided by R. And similarly, if we make the size of the Sun only a little bit smaller than the UK, up it goes again. If we make the Sun the size of a city, up it goes again. And the final dot in this graph is, what if we were to make the Sun only the size of a sphere of radius 3 kilometers? Then the escape velocity becomes 300,000 kilometers per second. The escape velocity becomes the velocity of light. At that point, no object, not even light, would be able to escape the surface of this object. So we talk about this 3 kilometer limit as being the event horizon that occurs at a particular radius, a so-called Schwarzschild radius. And so for an object the mass of the Sun, if we were to compress the Sun to a sphere of size 3 kilometers, it would become a black hole. But we're not limited to doing this only with stars. We could do the same thought experiment and say, what if we start with a body with a different mass? What if we started with the mass of the Earth? Well, then we would find that we'd have to compress the Earth to a sphere the size of order centimeters. If we compress the Earth to the size of a marble, it would become a black hole. If we were to compress the Moon, well, the Moon is about a mass of 100 times smaller, so we'd have to compress it to something like 100 times smaller in volume, smaller in radius, and so it would need to be smaller than a grain of sand in order to form the moon as a black hole. And if we took a mass equivalent to something like Mount Everest, we would have to compress it to something smaller than an atom in order to make that mass a black hole. So technically, any mass can become a black hole, providing we compress it enough. Now, we don't know how to do that. We have no idea how to compress any object, other than we figure that for large gravitational forces, some stars might compress themselves into small volumes. We've got no idea how we would possibly compress the Earth or the Moon or Mount Everest into a black hole. But just because we don't know how to do it, doesn't mean it's impossible. Okay, second piece of the jigsaw, now that we understand escape velocities. What did Einstein say about space and time? Excuse me for a second. Einstein said that space and the contents of space, in other words, objects with mass that might be moving with a certain energy, they are related. And rather than talk about the mathematics of how they're related, let's use the more prosaic description. Mass tells space how to curve, and space tells mass how to move. In other words, unlike Newton, who might say that, well, things moving through space, it's like the pieces on a chessboard, you can move the pieces around. Einstein says, well, if you move the pieces on the chessboard itself changes. What do we mean by mass tells space how to curve? How can space curve? Well, this is a rather tricky concept, mainly because it's fine if you talk about a piece of paper. All of us can imagine a two-dimensional piece of paper curving into a third dimension. That's, generally speaking, not a problem. But how can you talk about a three-dimensional space curving? Well, if you want to curve three-dimensional space, you really need a fourth spatial dimension to imagine it being curved. And of course, humans are not very good at imagining a fourth spatial dimension, because when we look around us, we see three spatial dimensions: forward, backward, left, right, up, down, and that's it. That's all we can perceive. Now, the mathematics is fine. The mathematics of 4 dimensions are no more difficult than the mathematics of 3 dimensions. But our imagination is somewhat limited. So Einstein developed the mathematics that explains how it works. Our imagination takes a little bit of time to catch up. And it's the curvature of space, the distortion of space, and indeed space and time, that determines how masses move. So we tend to think of things like this. We tend to imagine that the universe is two-dimensional, like a sheet of paper, and then imagine how it would be distorted by the presence of a gravitating body, a large mass, such as a star or possibly a black hole. And that's why we tend to often think about black holes, or at least in science fiction, they're often depicted like a funnel, because that's the two-dimensional equivalent, a two-dimensional funnel generated by distorting it into the third dimension. And like water going down a plug hole on letting water out of a bath, you can think of matter falling into a black hole in the same way. So it is an analogy. It's not supposed to be a good visual description. It's only an analogy. So why do we think that Einstein was right? If Einstein says that mass distorts space and time, why on earth should we believe him? Well, because general relativity has proved itself right in a number of different areas. For instance, the precession of the orbit of Mercury. In the little animation there on the left, you can see that the elliptical orbit of Mercury changes slowly over time. In other words, the ellipse doesn't go over itself time and time again. It's actually an ellipse that is slowly rotating around. So the closest point, the perihelion of Mercury to the Sun, is slowly precessing around. It's only a tiny amount, only arc seconds in a century, but it's something that Newton couldn't fully calculate. When Newton tried to calculate the precession of Mercury, he got a value which was only about 90% of its observed value. He couldn't quite get that last bit right. Along comes Einstein, and with his general theory of relativity, he calculates the precession of Mercury, and he gets it essentially spot on. Newton didn't get it right, Einstein did. This was one of the proofs that general relativity is basically replacing Newtonian physics as far as extreme gravity is concerned. Another example in which general relativity proved itself was observations of star positions, indicated by these little tick marks here. If you look at the star positions when the sun isn't in front of those stars, and then look again when the sun is close to those stars, of course that's only something you can do during an eclipse, otherwise the light from the sun would completely obliterate the faint light from the stars. So during an eclipse the positions of stars were noted, and the starlight is grazing the surface of the sun, and it was predicted both by Newton and by Einstein that the path of light would be slightly curved by the existence of this large gravitational field produced by the sun. Again, they both produce bending, but the amount of bending of light was different from the prediction of Newton and the prediction of Einstein in general relativity. And the observations agreed with Einstein rather than Newton. So again, an indication that we should take general relativity seriously. The idea that time slows down is a little difficult to get your head around. You can perhaps understand that light behaves a little differently and it distorts in the presence of the sun. But what about time slowing down? This was a very odd prediction of general relativity, so it was tested. Back in the 1970s, some accurate atomic clocks, here occupying one of the seats, were flown on commercial jets, and they were flown backwards and forwards and at different heights. Now, backwards and forwards gives you a velocity, and the special theory of relativity tells you how time slows down because of your motion. But in terms of gravitational field, that was something that they could calculate by flying at different heights, and by flying in different directions they could effectively decouple the effects of special relativity because of motion and the effect of general relativity because the atomic clocks were in a gravitational field. So these atomic clocks, some stayed on the ground, some were flown in aircraft, and then they were checked, and that verified that height makes a difference. In other words, the gravitational field in which the clocks are sitting does affect the rate at which time passes. This is actually quite important because atomic clocks are used all the time, even if you don't really realize it. For instance, there are separate atomic clocks in each and every GPS satellite. So if you're in your car or ship or aircraft and you're picking up GPS signals to tell you where you are, you're relying on the time difference between the time that the signal left the satellite and the time it's picked up by you. And the clocks in each of the satellites have to be synchronized. Not only that, you have to take into account the fact that the clocks in orbit are moving, and the clocks in orbit have their times changed by the fact that their gravitational field is not the same as a gravitational field at sea level where master atomic clocks are situated. So if that wasn't taken into account, the GPS clocks wouldn't be quite synchronized. And so special relativity and general relativity both have to be taken into account to make GPS as accurate as possible. So general relativity in the last 100 years or so has had plenty of opportunities to be tested, and each time it's been found to be, as far as we can tell, correct and more accurate than Newtonian physics. One of the very odd predictions of general relativity is gravitational waves. In other words, objects that are very massive, moving very fast, will not only perhaps generate the sort of things we're used to. Some objects might generate light, for instance, of different wavelengths, but massive objects will also distort the space around them and produce gravitational waves. And these gravitational waves produce a very odd result. If we imagine a cylinder and imagine a gravitational wave moving through that cylinder from right to left, then if the cylinder originally had a cross-section that was circular, then as the gravitational wave moves through it, the circle will stretch in one direction and then the other, and then one direction and then the other. In other words, the circle will distort into an ellipse backwards and forwards, backwards and forwards. Now, these distortions are nowhere near as large as this little animation would indicate. It was calculated that if we have a very dramatic situation like, for instance, two black holes smashing into each other, that will produce a substantial set of ripples in space. But if it happened a long way away, we wouldn't expect to see any appreciable distortion of space. Not the 10% indicated by this little animation. The distortion wouldn't be 1 part in a million or 1 part in a billion. The distortion would be something like 1 part in 10 to the power 20. Absolutely tiny. And hence it was a prediction of gravitation, a prediction of general relativity that gravitational waves would exist, but they were considered to be just, well, fanciful, because there is no way we'll ever be able to measure anything so small. So this was a prediction that was essentially forgotten back in the early 1900s, but we'll return to it shortly. So we've seen escape velocity and we've seen general relativity. Let's have a think about stars and galaxies and where black holes come from. Well, we are fairly convinced that massive stars that come to the end of their lives might collapse, and the core collapse of a massive star might result in a supernova, in which the radiation in the core of the star supporting a massive star, when the fuel runs out, the core collapse and all of the mass outside collapses into the core. It rebounds and produces an enormous shock wave, which we call a supernova. And it might be that if the mass of the star is large enough, it might compress the central core of the star until its mass and radius are such that it meets the criteria for a black hole. If a black hole of a stellar mass does exist, then you'd expect, if you get too close to it, to get yourself ripped apart by the tidal forces. This animation shows what you might expect when one star gets too close to a black hole. Just like water going down a plug hole, the water doesn't all go down the plug hole at the same time. The water tends to circulate and, as it were, wait its turn. Let's just run that animation one more time. If there's a black hole here and a passing star, if the black hole has very large tidal forces, it can rip a star apart, and the matter from that star is trying to go down the black hole, but it's waiting its turn, getting very hot as the matter circulates before getting swallowed by the black hole, and the circulating matter gets very hot and radiates visible and possibly even X-rays. Notice that in this particular animation, not only do we have a lot of swirling matter, the accretion disk, we also have these rather enigmatic jets coming out. Now, we think those jets exist, but we're not altogether convinced of the mechanism by which those jets are convinced. So the accretion disk itself occurs because matter can't all go down the black hole at once. And this idea of the tidal forces being so strong in the close vicinity to a black hole, ripping things apart, is called spaghettification, or if you prefer, the noodle effect. So lots of systems are being studied that appear to have accretion disks and appear to have jets, and trying to understand exactly what the mechanism is does it involve magnetic fields as well as the very strong gravity, and what exactly produces these jets? What are they made of? As well as X-rays, what particles are involved and how exactly do they form? If we have a look at what's going on in the centre of the Milky Way, we find what we believe to be another black hole, but a different type of black hole, one that is much more massive. For the last 10 years or so, stars have been studied close to the centre of our galaxy, and if we watch this star here over a period of years, we find that star gets whipped around something that we cannot see. There are a number of stars that are in elliptical orbits. They seem to be obeying the sort of rules we would expect for Keplerian orbits as indicated by Newton and Kepler. But these objects appear to be held in place by a very massive object. And it appears to be a supermassive black hole because it is very massive but very small. Otherwise, those stars would collide with it. And by looking at the orbits of these stars, it looks like the supermassive black hole at the centre of our galaxy has a mass of some 4 million solar masses. This symbol here, capital M circle dot, is just shorthand for the mass of our Sun. There's nothing particularly interesting about the mass of our Sun, it's just a convenient unit rather than using kilograms or tons. So the black hole at the centre of our galaxy that is responsible for stars orbiting very quickly appears to be 4 million solar masses. And if we know its mass, we can work out what its maximum radius must be. Remember, the escape velocity depends on the mass divided by the radius. So if this is a black hole, we can calculate the radius. And that's the solar system, just to act as a scale. Let me just dim that down slightly. When we calculate how big the supermassive black hole is, it's much bigger than our Sun, but smaller than, for instance, the orbit of Mercury, just to give it a scale. It would appear that there are supermassive black holes at the centre of most, possibly even all galaxies. Galaxies are being studied to find just how many supermassive black holes do exist. But some supermassive black holes are indeed much larger than the one at the centre of our galaxy. 4 million solar masses might sound like a lot, but in the Andromeda galaxy, the supermassive black hole at the core of that galaxy appears to be 250 million solar masses. That would mean that the black hole is about the size of the orbit of Mars. In the Sombrero galaxy, M104, the supermassive black hole has a mass of about 1 billion solar masses. That would mean that the size of the black hole must be larger than the orbit of Uranus. And the largest black hole, well, the record breaker keeps changing, but if we take a very large supermassive black hole at the centre of one or two galaxies, then we find that it's more than 20 billion and too big for my diagram. You can get the rough idea of scale from that little bit of the black hole in the corner there. We're still trying to understand where these supermassive black holes come from. Presumably they're different from the black holes that form when stars come to the end of their life. A massive star comes to the end of its life and forms a black hole which might be a few solar masses. But how do you get to be millions or billions of solar masses? Are they made in the centres and then galaxies form around them? Or do galaxies form and then black holes start forming? One of the jobs of the James Webb Space Telescope is to look at very early galaxies to try and figure out whether the supermassive black holes at their cores came first, or the galaxy comes first, or whether the black hole and the galaxy evolve at the same time. Interestingly enough, the Hubble Space Telescope has looked at various star clusters within our own galaxy and has found massive black holes even at the centres of star clusters, not at the centre of the galaxy itself, but simply at the centre of star clusters that might contain thousands or tens of thousands or hundreds of thousands of stars. And that begs the question, well, we've seen it in this star cluster, but does it mean that all large clusters contain a black hole at the centre? Well, that's again an ongoing area of research. So we've looked at escape velocity, we've thought about general relativity, we've thought about stars evolving into black holes and the supermassive black holes at the centres of galaxies. But how do we know they're there? Partly the evidence is what I've shown from stars moving in particular ways that indicates the presence of a very massive, very small object. But recently, a second way of detecting the existence of black holes has become available to us. We can detect gravitational waves. So it started with an observatory called LIGO, the Laser Interferometry Gravitational Wave Observatory. And this map here says that the original LIGO, there was a large observatory in Washington State and another almost identical observatory in Louisiana. They built 2 of these observatories, simply because if you build one and you get a result, nobody will believe that you've actually seen gravitational waves unless you build 2 a long way apart, 3,000 kilometers apart, and get the same observation in both. So what is a gravitational wave observatory? It's effectively a laser source that gets split into 2, and the laser is sent down this 4-kilometer arm to a mirror at the end and then bounced back. The other half of the laser goes along the other arm, bounces off a mirror and comes back. So you can see this characteristic L shape, 2 long arms, 4 kilometers long, each of which has got a mirror at the end. The mirror has to be kept isolated from the ground, otherwise if the ground shakes, the mirror moves. And what we're trying to do is determine whether or not the lengths of these 2 arms change. Remember what I said about a gravitational wave passing through a cylinder? It'll squash one way and then extend, then squash, then extend. So if we think about the lengths of these 2 arms, if a gravitational wave passes through the observatory, one arm will become slightly longer than the other, and then vice versa, and the lengths of the 2 arms will change backwards and forwards, backwards and forwards. And the differences, remember, are going to be tiny. So we don't want the mirror at the end of these arms to be subject to, for instance, earthquakes or a door slamming or somebody walking close by or a train going by or any other seismic events that could make the Earth change position. So the mirrors at the end are sending the light back down to the original laser position, and these mirrors are held in these sort of pendulum arrays to try and isolate them from movement of the Earth. When the laser gets back from the mirrors at the 2 ends, the 2 light beams are combined. If the 2 arms are slightly different length, then the length of time it takes to go down one arm and back again is going to be slightly different than to go down the first arm and back again. And it will be slightly longer for one, then longer for the second, then longer for one, then longer for the second. It'll be back and forth, back and forth. So there will be tiny variations in the travel time of the laser going down the 2 arms. And this very complex interferometer that I'm showing you here is designed to pick up these tiny changes in the light travel time for these 2 arms. 4-kilometer arms, but the distances we're trying to measure, the change in the position of the mirror, are much, much, much less than the diameter of an atom. And so we want to be sensitive to changes of that magnitude over a distance of 4 kilometers. You can see that it's a very technically challenging experiment. And yet, in 2016, it was announced that they had detected gravitational waves from data taken in 2015. Took them quite a few months to analyze. But what they found was a signal. It might just look like a random set of wiggles at the bottom there, but it is a very telling signal. Let me just separate it out into the signal from the Washington State detector and the signal from Louisiana. If they only had one of these, nobody would believe that it was real. But these 2 detectors, 3,000 kilometers apart, appear to pick up the same wave. Have a look at what it's actually saying. It's effectively noisy, and then it's picking up a slow variation whose amplitude is getting larger and larger and larger and faster and faster and faster, and then dum, it's gone. And each of them show the same variation. They're superimposed at the bottom here. The vertical scale is labelled as strain. In other words, how much longer is one arm compared to the other arm relative to the arm length. The strain is measured in units of 10 to the minus 21. 1 part in 1,000 million. In other words, over a few kilometers, it's equivalent to the diameter, not even the diameter of a proton, not even the diameter of the nucleus of an atom, much, 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 much less than the diameter of an atom. And yet those variations, a little bit noisy, but those variations do appear to be real and do appear to be reproduced from one detector and the other. And the wiggles may not look much, but a theorist can take these wiggles and say, what possible event might have produced wiggles that looked like that? And they came to the conclusion that what they were looking at was the distortions in space resulting from two black holes, one of mass 29 solar masses and the other of mass 36 solar masses, two black holes orbiting each other, combining, merging together, which is the final result there, and then settling down to a black hole of 62 solar masses. Those of you who are good at maths will realise that 29 plus 36 doesn't equal 62. The resulting black hole appears to be light by 3 solar masses. 29 plus 36 gives 65, but the final black hole is only 62 solar masses. It was calculated that 3 suns worth of matter, 3 solar masses, were converted into gravitational waves. Think about our sun. Our sun is converting mass into energy. By the time the sun is at the end of its life in another 5 billion years or so, by the time it gets to the end of its 10 billion year lifetime, the sun will have used up 1% of its fuel. So 1% of a solar mass is converted into energy, and that's been keeping the sun going for 10 billion years, or will keep the sun going for 10 billion years. Here, 3 solar masses have been converted into gravitational energy. And I didn't point out the scale, but there it is. The scale in time is just a fraction of a second. So 3 solar masses were converted into energy on a time scale of a few tenths of a second. Compare that to our sun, which converts a fraction of that energy slowly over a period of 10 billion years. So this particular event of these two black holes merging with each other, which are thought to have occurred something like 1 billion light years away, this merger of two black holes for that fraction of a second produced more energy than all of the stars in all of the galaxies of the known universe for that fraction of a second. In other words, this event was more energetic than everything else put together for that fraction of a second. That's why it was possible to observe it. It was an absolutely phenomenally energetic event, and we could see it even though we are 1 billion light years away. The fact that the technology allows you to do that is truly phenomenal and worthy of a Nobel Prize. More gravitational wave observatories are being built in other countries, and there are plans to build one in space. Why limit yourself to having laser beams that go back and forth along a 4-kilometre tunnel, which is what you're limited to on Earth, depending on how long you want to build these tunnels? If you go into space and have 3 spacecraft, you can fire lasers back and forward between them, and you're not really limited as to how far apart you can have your spacecraft. So there are plans to have 3 spacecraft in a triangle like this, and you can have them millions of kilometres apart. So the arms, instead of being kilometres long, will be millions of kilometres long, and they will be able to see gravitational waves of much longer wavelengths. So LIGO is sensitive, as we've seen, to waves with periods of a fraction of a second, which means it can see black holes merge or neutron stars merge. But ELISA, this laser interferometer space antenna, will be sensitive to much longer wavelengths and much longer periods, things that happen on timescales of seconds to hours rather than fractions of a second. So it means that ELISA can detect signals from black holes, perhaps within our own galaxy, but it might also be able to see supermassive black hole mergers in other galaxies. It's also hoped that it will be able to see the gravitational waves created by arguably the biggest singularity of all, the singularity that occurred, we think, at the Big Bang. So ELISA will take a little while. The technology is being proven. It will probably be next decade before this interferometer is up and running. Meantime, we can check on what's going on around black holes using the Event Horizon Telescope. This is existing radio telescopes that have been networked together to form a very big interferometer, the ones shown here across the face of the Earth. When they were all pointed at the supermassive black hole at the centre of the galaxy M87, this is thought to be a black hole with a mass of many billions of solar masses. They saw this result. What we're looking at is an accretion disk. There's a shadow in the middle because, unfortunately, because of the black hole, light can't escape from the region around the black hole because the black hole's gravity is so strong, it tends to bend light waves such that there's always a shadow somewhat larger than the event horizon itself. We can get a feeling for what we're looking at from this little animation. So if we imagine a pancake of an accretion disk swirling around, if we look at it from the side, we expect to see something like the rings of Saturn, very thin. Look at it from the face, we see a swirling mass. But you can see the side view doesn't simply look like the rings of Saturn, because the rings at the back are still visible. They get bent by the very strong gravity of the black hole over the top of the black hole so that the back of the accretion disk is actually visible. Not only that, but the underside of the disk is also visible at the back because, again, light from the back of the ring is being bent by the extreme gravity around the black hole. So we actually get to see the sides of the accretion disk and the back from above and from below. We have to get used to the fact that things are so extreme around a black hole, things are never quite what you think. And we think that that's why we see effectively a donut around M87, regardless of whether or not we're looking at the accretion disk face on, or whether we're looking at the accretion disk side on, we would still see something that looks like a donut. In this case, it's brighter on the bottom than the top, so we think we're looking at the disk slightly edge on. M87 was chosen because it's a very big supermassive black hole with many billions of solar masses, much bigger than the supermassive black hole at the centre of our own galaxy, which is only 4 million solar masses. So our galaxy's black hole is much smaller, but it is a lot closer. So its size on the sky is actually not that different. So in terms of resolution, they figured they may as well take data from both of these sources, and it took them a little bit longer to analyse the data from Sagittarius A star, the supermassive black hole at the centre of our own galaxy, but again we get a characteristic donut. It took longer to analyse the data from our galaxy simply because it's a much smaller accretion disk and everything is moving much faster, so you can't simply average the data from one night and the next night and the next night of observing, because things might be changing on a timescale of hours. So it was more problematic, it was more challenging to analyse the data from Sagittarius A star. It took them a little longer. But again, we see a donut, and again we see some intensity variations. Although they look the same size on the sky, we have to remind ourselves that these two donuts are very different in size. The donut from the M87 accretion disk is similar in size to our solar system. There's Pluto's orbit for comparison. Whereas Sagittarius A star, we'd have to blow up that very central region, and the donut that's in the accretion disk around our supermassive black hole is a little bit less than the size of Mercury's orbit. So we've looked at escape velocity to understand what that means. We've thought about how Einstein said that mass distorts space and time. Thinking about stars and galaxies tells us that massive stars might form black holes at the end of their lives, and galaxies have supermassive black holes at their core. And gravitational waves, despite sounding very fanciful in terms of the technical requirement of seeing changes to space that are only 10 to the minus 20 or so parts in one, despite that, it is still possible to see these gravitational waves, and that's one of the more than one way we can detect gravity. Let's have a think about what science fiction tells us about black holes. Does Hollywood ever get it right? I've chosen 3 films which depict black holes in one way or another, either as the central theme or just in passing. The first one is Disney's The Black Hole. Not sure you remember this. Anthony Perkins and Ernest Borgnine and Maximilian Schell in this Disney film about black holes. The second one, a little more recent, Lost in Space. And the third one, Event Horizon. So what's the black hole connection in these 3 films? Well, the statement is that in the black hole, a ship is parked right next to the event horizon. Time stands still at the event horizon. Therefore, the idea was a person has taken a ship, gone to the event horizon of a black hole and put the handbrake on, and is just sitting there observing the black hole and making measurements and doing some science. Okay, what's Lost in Space? Well, it's nothing to do with the plot, but towards the end of the film, the spacecraft is trying to escape from a planet. It is quite happily escaping from the planet, but then, for whatever reason, the planet decides to implode and form a black hole. When the black hole is formed, the spacecraft suddenly gets pulled backwards. Event Horizon, what's that all about? Well, it's about a ship that is powered by an onboard black hole. Okay, 3 films with 3 scenarios. 2 of them are rubbish. 1 of them is physically plausible. I'll give you just a few seconds to think about which is which. Okay, the first one is rubbish. Yes, time stands still at the event horizon of a black hole, as seen by an observer who's a long way away. In other words, an object that appears to be falling into a black hole will appear to get slower and slower and slower and move more and more slowly towards the event horizon. That's as seen by a distant observer. If you're on the ship that's falling into a black hole, you just go straight in. You don't perceive that time is coming to a standstill whilst you do your scientific experiments. It doesn't work that way. Time is relative, so you always have to ask about time relative to an observer, and time standing still is relative to a distant observer. So the scenario of the black hole film is rubbish. What about Lost in Space? They're pulling away from a planet, and they're pulling away apparently quite happily, but then the planet collapses into a black hole. Well, regardless of how likely that is, bear in mind that when an object collapses, effectively the same mass is still there. The mass doesn't go anywhere. As far as we know, the mass is still there. We can weigh black holes. Remember, the black hole at the centre of our galaxy is producing the orbits of stars. It is definitely having a gravitational influence because of the mass that is there. So if the planet collapsed into a black hole, the ship would still be in the same gravitational field. It would be at a particular distance from a particular mass. The fact that that mass is more compressed makes no difference. It's like saying the Earth is going round the Sun and it's being kept in orbit by the gravity of the Sun. If the Sun were to compress into a black hole, then the Earth wouldn't realize that. It would still keep on going and it would orbit the sun in 1 year because you'd have the same mass at the same distance. The fact that it would be compressed into a smaller volume doesn't make any difference as far as the Earth was concerned orbiting the sun. The same for the spacecraft leaving the planet. If the planet collapsed into a black hole, the same mass would be present. The ship, if it could escape in the first place, could still escape even if the planet became a black hole. So that one's rubbish as well. So, event horizon. Yep, that's the plausible one. Can you power a starship using an onboard black hole? Yeah, no reason why not. Is it possible? Well, I'm not sure how you do it, but yes, it's possible. If you have a black hole with a mass of less than, let's say, 1 kilogram, then of course not much energy is available. The maximum amount of energy you can expect to get out of anything is E equals mc squared. If you had 1 kilogram to start with, you would only be able to get something like 1 kilogram times speed of light squared. It's a large amount of energy, but it's not enough to get you across to the stars. If you have a very large black hole, so a black hole with a mass, let's say, of more than Mount Everest, then Hawking radiation is very weak. What is Hawking radiation? That's the radiation that's hypothesized to be radiating from every black hole. It's only a hypothesis, but everybody seems to pretty much agree that it ought to exist. According to our understanding of physics and quantum mechanics, then we would think that particles are being radiated not from inside the black hole, but just from the event horizon itself. Technically from just outside the event horizon, we would expect a continuous radiation. And the radiation is dependent on the mass. Very large black holes don't radiate much. Very small black holes do. So if the black hole was too massive, the Hawking radiation would be very weak and difficult to use to power your starship. But something intermediate would work very nicely. If you had a black hole with a mass of, I don't know, 1 million tons, let's say, the power in the Hawking radiation would be phenomenal. It would be equivalent to the output of 100 million nuclear power stations. In other words, if we take a nuclear power station as something that generates 1 gigawatt, then it would be 100 million gigawatts of energy at your disposal. Not only that, but the black hole would indeed radiate and eventually disappear, but it would last for about a century or so. So you could power your starship, you would have huge amounts of energy available to you, and you would only need to replace the black hole every century or so. How you would build a reactor to use that, I don't know, but that's a technological challenge, not a science challenge in the sense that the science is sound, the technology doesn't yet exist to do it, but the science doesn't break any laws of physics. So the radiation from such a black hole, which remember 1 million tons, it wouldn't be big, this black hole would be smaller than an atom, your engine room wouldn't need to be very big. The black hole, if you could capture and direct the Hawking radiation, then you'd have enough energy to power your starship. So event horizon, in that sense, was a perfectly reasonable plot. What about the other staple of science fiction writers? The idea about shortcuts through space, wormholes. Not only shortcuts through space, but if you distort space and time, doesn't that mean you have a shortcut through time as well? So are wormholes possible? In other words, instead of having a funnel that looks like a black hole, could you end up with 2 funnels back to back, such that you could go from one space to another space? Well, science fiction writers seem to have used this all the time through Stargate and Contact and Star Wars and Star Trek. There's no lack of science fiction in which wormholes, regardless of what you actually call them, get you from one point in space to another without all of the boring speed of light travel from A to B. But if it is possible to take a shortcut through space by distorting space, and arguably that ought to be possible If you can get the right mass in the right place to distort space in the right way, maybe you can have a shortcut through space. But what about a shortcut through time? Is it possible to have time travel? Well, again, there's no lack of different people who've hypothesized. If you're of a particular age, you may relate to the time machine in the bottom left or possibly the bottom right. More recently, Back to the Future type plots. But of course, every time you have time travel, you have a paradox, whereby what if you go back into the past and change history? Well, Hawking had a proposal, a conjecture. And it is a conjecture because there's no way he could prove this. But he figured that if wormholes are possible that would allow you to go back in time, then he proposed the chronology protection conjecture, in which the wormhole that might allow time travel would collapse before anything has actually got time to travel through it. In other words, that's one way of keeping the universe safe for historians. Purely conjecture, and the answer is we don't know. There are too many paradoxes related to time travel. But according to our understanding of the way matter and energy distort space and time, then perhaps it is possible. But we do have a problem, and it's a big problem. General relativity works really well for massive objects, like objects the size of stars, black holes that are star-sized, or millions of stars. General relativity has been with us for more than 100 years, and it's worked really, really well. But so has quantum mechanics. Quantum mechanics works really well for tiny objects, like atoms and molecules or subatomic particles. And I'm not saying anything about how quantum mechanics works, but these are the two foundations of modern physics: general relativity for massive objects and quantum mechanics for small objects. But what if the object is massive and tiny? For instance, a massive object like a black hole. And we don't quite know how big it is. We know how big the event horizon is. Maybe the object itself inside the event horizon is even smaller than that. So if we want to understand black holes, we need general relativity and we need quantum mechanics. So that means we need quantum gravity. We need to get these two theories together. And that's where the problem is. No one has successfully melded together general relativity and quantum mechanics. They are not good bedfellows. Whenever you try and build a theory that encompasses both of them, you get infinities or things that simply do not work. A universal theory of everything has proven to be elusive. Einstein never really believed that quantum mechanics was the right description of the microscopic world, and he spent a long time wrestling with his theory of everything. Special relativity was very successful. General relativity was very successful. He spent decades trying to work on a theory of everything. And it turned the handsome young man that we can see on the right there into the vision of Einstein that we all know and love as an old man. If a genius like Einstein could not get his head around the problem, then what will it take? Well, maybe it'll be some unexpected discoveries from LIGO or the other observatories that are being built on Earth, or maybe the gravitational wave observatory that will ultimately be built in space. Maybe results from those observatories will point the way for a better understanding of black holes. Thank you for listening.